have respected experts, respected staff members present here, respected audience. I'm presenting my PhD seminar on a topic induction motor fault diagnosis by transient current analysis using advanced digital signal processing techniques. First few slides I will give an environment of the problem. Then I will focus on what is the motivation for that. After that, I will go through.
Why do you have to do the text advanced?
Advanced digital signal processing.
What is the
because the whole first previous methods like Fourier transforms and all those things are now replacing with some upcoming mathematical transforms, and I'm using those for this. Looking at the environment of the problem, I've selected typically, if we look at the entire mechanical field where the rotational energy is used, roughly 2/3 of the energy of entire world is used for the motors. Say roughly 46% motors are used in worldwide, and approximately 90 to 95% of that 46% is used as induction motors. So I am typically concentrating on induction motors. Say why induction motor? Because it's a cost effective. Then there is no any sparking or anything after. The rotor is very easily manufactured. No electrical part major on the rotor. So this is the selection and the base top speed characteristics also available for that. Going through the typical faults, electrical faults, actually I am not considering for my concentration focus, but the faults can be tackled with DSP processes. These are the electrical faults, those are occurring in the induction motors. Typically, as a research, I have to focus on one particular fault and get some solution at a prior level. So, through mechanical faults, say mass unbalance, the broken rotor bar, air gap eccentricity, rotor winding, stator winding. Actually, air gap eccentricity also finally gives some impact on the bearing. So, if we go through a statistics, still further focus should be that the one fault which is on the higher side should be selected. So if we go through our induction motor fault statistics, we come through that the bearing fault is maximum in this, and that is 40%. So my focus will be on typically the bearing faults in the induction motor. This is another statistics gives us about how the faults are occurring in typical machines. If we consider all motors is 166, but induction motors, as those are used for 95%, the fault 155, 2 faults are occurring in that. So we should concentrate more on that. These are typically fault nature, how it occurs. Then these are the, as per IEEE and EPRI, the fault statistics are very fault related, are further more, so concentrating on that. Actually, going through little detail about why these faults occurs. Say excessive loading, directional loading. So if motor, sometimes bearing is designed only to rotate in a clockwise or anti-clockwise. So that loading creates a problem. If we go for anti-clockwise for some time, it creates a problem. True brenneling and false brenneling, most other problems are say usual. True brenneling and false brenneling is the typical characteristics. Say true brenneling means, say sometimes the ball is sliding over because of high loading condition and that. So that causes a true brenneling, and false brenneling means sometimes there is grease is not there, and because of that it gets slides. Finally, we are making an impact on outer or the inner rails. So these are the faults. What is health monitoring? Say in old days, before say DSP or signal processing or some methodology, say usually the breakdown faults was tackled on the major side, and say health monitoring means like a routine checkup of ourselves. We go to check our say blood pressure and all that. Similarly, motor has to get routine check, so we can forecast about which are the problems may occur in that motor. We should keep some specific breakdown time for that. So before going for breakdown, we can recover all that. That is the advantage of this. So health monitoring gives us a prime importance activity because it gives say reliable and less time consuming activity, algorithms used for most of the faults, and lesser computational burden. we can easily tackle those problems in a faster way. So this is the motivation behind research. Then I will go through a literature survey. Say there are two types of techniques usually used in motor. One is called as invasive sensor technique, and second one is a non-invasive sensor technique. Say invasive means something sensor is injected in the motor design itself, then it is called as invasive. So it needs at a design level itself, it needs some sensors to be implanted in motor, and that creates another cost of that sensors and the overall system. If something happens to that sensor, replacement of that sensors and all those things creates a problem. While a new advanced techniques we can go for, which is a non-invasive type, so no additional space required, with routine checkup like a current or voltage or whatever the say vibration, by checking all external things we can go for that. So conventional methods which are available are thermal monitoring. So you place a thermometer inside and get various temperatures at various parts and get back. Then magnetic flux monitoring, so air gap flux can be monitored and that can be checked. Then vibration monitoring. Then partial discharge. Partial discharge also electrical insulation levels can be checked with partial discharge. But discharge level should be controlled, otherwise it may permanently damage the insulation. That precaution has to be taken. So these are all old methods. Then noise monitoring. The say in case of typical induction motors in the bearing industry like escape and all those things, still they are very well reliable on the noise monitoring of that machine or vibration monitoring. That is the basic aim of this. Say I am concentrating on the typical electrical side of that, and current monitoring is also nowadays upcoming method for investigation. Say there are a few advanced monitoring systems. Say MCSA, that is motor current signature analysis, then surface vibration analysis, instantaneous power signature analysis, angular speed, and extended pass vector. These are also the methods. I am typically concentrating on the motor current signature analysis for that. Say after the researches, it comes to a significance level of that, and in this significance level, the high significance level is for MCSA. But for bearing faults, just now the vibration is used as a high significance level. I am trying for my studies to convert this MCSA with some advanced techniques to be get for bearing fault handled very perfectly. Usual system is this way. Data acquisition is done with certain current or say current inspection. Then from that current, a feature is extracted with some certain method. Once the feature is extracted, those parameters, fault progression and particular analysis is done using some classifier. That problem is classified and identified that this problem is there and this problem is not there. This is a usual method for that. Actually, this is the general setup used for that. Say any machine, I have to use some Hall effect sensor or some sensors I have to check for to get a current or respective mechanism out of that. Then that is the data acquisition. That data acquisition, okay, if we clearly check for the induction motor, while going through a mathematical equations and all, I come to know that a simple rotating magnetic field can be compared easily to understand for non-electrical persons. Like we can compare this with simple Mexican wave. If we go for a football match and check three stadiums are there, if you assume and three persons are making hands up and down, motion can be considered as an alternating, and the effect of three hands rotating at three different levels, it is as like as the wave is moving on a stadium. So it is similar to a rotating magnetic field. Say if we further go for, if something happens and the one of the person is not moving hand in that typical fashion, then we can say that some hurdle is observed on that 50 Hz cycle or rotating magnetic field synchronous speed. Certain additional impact is observed on that, and that can be identified using some digital signal processing. This is what the ultimate aim is. This is also a good method if we check for RMS value. Then higher order statistics, so skewness and kurtosis. This is all literature survey that gives that few other methods are already invented on. Say time domain analysis, frequency domain. I'll go through a typical 2-3 analysis which are more interest of my field just now. So this is a parts vector, already proven. I'll skip this. So time domain analysis, the fundamental frequency can be tracked, sleep measurement is also done. So this is also a time domain analysis. So I'm checking for at exact time what is happening. So if you check out for a Fourier transform also, say in a time domain, I'm just checking what frequencies are coming, but time domain is a very large domain. So problem with I cannot key point that small windowing of it. So it is also Fourier transform frequency analysis. I'll skip for literature separate. These are the examples where the Fourier transform is just now used as per the literature surveys. This is time frequency representation. In time frequency representation, I can go for any other methods. Time frequency distribution is checked. So this is what the frequency and the time. I'm checking on both sides for getting my results. A good option for time frequency is Weber transform, and beginner distributions are all this. Short-time Fourier transform is also used where the windowing is carried out, and that gives also good results. This is also wavelet analysis and all this. I'll skip this. Now this is discrete wavelet transform. I'm just considering once again this for this process. Actually, in a wavelet transform, what we are actually carrying out is I'm using the two filters, high pass filters and low pass filter. And the high pass filter, by using that, the noise is removed every stage, and I'm going by stage. I'm constructing my own signal and reconstructing it with all the noise, higher noise removed out. This is done in wavelet. This is the same thing, low pass filtering and high pass filtering. These are the DWD DSP process family. So time and frequency both scale is handled by wavelet, and I'm using the same thing as my focus in this. WG performance is also really good for signal, and one of my phases I'm going to use this. So this is also as per the literature. Now I'm coming to a proposed work. What exactly I'm trying out? So actually I have already set up my test bench where I can load that motor as per my requirement. I'm getting my speed changing as per the load. Then the fault are to be simulated. So for typically bearing fault, I am going to simulate that fault in-house, and I'm checking with a no fault and fault. Two conditions will be available to me, and I'm getting the current signatures of that. That will be analyzed, and then finally I'm coming to the conclusion that which method is the best for bearing fault for handling that current signature. In proposed work, few transforms are also verified, and those Hilbert-Horn transform and further beginner-willing is also discussing. So this is actually a block diagram. This way, I'm working with entire project is set up in research is done in this way. So motor fault typically considered as a bearing. Then the in-house, I'm using some sensors to sense the current. Actually, for prerequisite in first year, I have tried for usual CT to dig out the current, but looking at its saturation level and the flux level, it was not suited well. Then I shifted from current transformer to clip-on THS 720 CRO, and I have tracked few observations from the clip-on current probe. Still, it was not feasible to get actual digital samples converted into that. So further, I have gone through a Hall effect sensors and finally concluded that the Hall effect sensors are better for this, and use all my current sensing using Hall effect sensors. Then there is a signal processing. I have used two approaches. The first approach, for characterizing, I am using wavelet transform. Then for second condition, second phase, I am going to use Hilbert vibration decomposition with SPWD, smooth pseudo beginner value distribution. This will be the classifier. This will be a typical identifier, and the fault detection is later on do using neural network. And for second case, I am using the support vector mechanism to identify which is the fault condition and which is not a fault condition. For this, I have as a backup two conditions with a faulty bearing and with a non-faulty bearing. So those things are working. So actually, in-house we have developed this type of, this is our first product bearing. So this type of fault is generated on the bearing. Actually, the outer race is very hardened one. To tackle with the outer race, you need a carbide drill to get that. By knowing actually the size of drilling, that also actually not coming in interest that how much fault I am creating on that. So I will try for different bearing faults, and then to come back to this is a low level fault and high level fault classifier, and then I come with this. So typical, I am handling outer race, discrete defects. A few basics about this. The bearing can be considered as with the contact angle of the ball, usually considered 0 for that. Then the ball diameter and other detailings of bearing. So actually, mechanically, your say bearing characteristics, frequency characteristics is already identified by a few of the researchers, and this is the direct equation that the characteristics frequency is obtained from that equation. So this is typically details about the inner ring rotational frequency, then fundamental frequency, outer, then ball frequency, all can be known. Then this is outer race waviness, outer race discrete effect. The frequencies are already identified by the researcher. I am using the same one for my analysis. This is a theory actually given which gives us about what is a gap, air gap flux and permeance of that and how it creates with typical fault nature. So this is the equation which gives you gap variation, air gap variation, angular position. So typically the parameters use 1 for a stator, 2 for a rotor, ST that is a static eccentricity, and dy is a dynamic eccentricity. So all components are included into that, and which gives us typical average air gap analysis. So this gives a permeance available in the motor. Then this gives an actual later on after few these equations I am coming to actual bearing frequency, which can be identified in the current signature and which gives us actual result. This is a test setup. This is I am having in my lab. Actually, this is an induction motor. This induction motor is coupled to a DC generator, and this DC generator is further coupled to a tacho generator. Actually, not getting in picture. Tacho generator give me a speedy feedback. Actually, I am not using that for my research because I have a separate tacho generator. I am using a speed measurement using that. Actually, say in electrical lab, we can use with a mechanical load also, but the characteristics is not detailed. So first thing what I have to do is to find out the efficiency nature of this generator, and that generator electrical output I will convert it into mechanical, and that will consider as an output of the motor for considering the loading condition of the induction motor. This is a rating for motor which I have used for my setup. This is actually a bearing with a fault. So this type of various faults are created on the bearing which will be considered as a faulty condition bearing. And with this, a new fresh bearing which will be ideally working for, that will be another data set which will have a non-faulty bearing set. This is a bearing type. Usually for induction low rating induction motors, the bearing uses SKF 6203Z. Z is it's covered or uncovered. That is a typical characteristic. It is having 8 balls. Each diameter is given. Ball diameter is 6.35. Speed for this motor is 1200 RPM. Frequency is 62.92 is the outer race frequency. This frequency BPFO is calculated from the mechanical equation that we have checked for the bearing analysis. The outer and the say lower side band and the upper side band for the vibrations can be calculated from this equation. These are the calculations for that. This is the equation used for calculating band frequencies. This is ABB EL25P1 is a 25 ampere Hall effect sensors. This I am using it for a current extraction. Actually, lower motor rating is a 5 ampere. I cannot go for direct 5 ampere Hall effect sensor, was not available for me. So another technique can be used, which is used in this, that you can add the number of turns on this sensor, so it works like a CT. So in terms of primary size, I have increased that. So I converted that 25 ampere sensor, converted down to a 5 ampere sensor. And using that, a secondary side current will be in milliampere, which is proportional to have all my current signature included in the stator side to the reduced level, and that I am going to capture using some type of this is a Hall effect sensor design. So actually the secondary current will be dumped in the resistance, and the voltage across that resistance will be the voltage proportional to the current signature which is available on the stator side. This is Hall effect sensors rating. This is a conditioning circuit for Hall effect sensor. This is a sensor testing. So sensor testing is done for what current, what is the voltage in RMS voltage in millivolts. The same. This is actually the load. By adding a various load, I have a separate speed conditions obtained for the motor. This is a motor current, motor voltage, motor current, power, which is input side power observed. This is a DC motor connected to that, so load connected to that, and the multiplying factor for the power. Okay, this is for healthy bearing, and this rating for faulty bearing. So actually it is a rigorous process. For first week I have tried with a non-faulty bearing, go for all sets of readings. After that, using the person, you have to pull that bearing from that machine, use another bearing which is drilled, that is a fault is created on that we have to fix on the motor, and later on that motor is retested for the same type of load and the other categories. This is actually a first result. I have used a DAC card to get those results converted to a digital, and that DAC card gives me this type of first waveform for faulty bearing. This is a DAC acquisition card. I have used NI USB 6009 card, which gives a nice characteristics, and at a higher sampling rate also I can use for that. This is specification. This is a card. Actually, multiple in-outs IOs are available, but I will use only for one motor current use out. This is that acquisition. Actual project, actually research work. This is a prerequisite required for the actual research work. Now research work is now split into two phases. Now I have a current sensing data available with me. I have two sets of data. One is I am knowing that data is not having any fault, and the other is I am knowing that this is a faulty bearing data. And these two using feature extraction for first phase I have done with a discrete wavelet transform. Say within using the steps 1, 2, 3, 4, I could not get a fault. So after 5th level, the fault is very well classified. We will come to it later on. And the classifier used for first thing is artificial neural network. For second phase, I am using Hilbert vibration decomposition with Wigner wave. Actually, basic thing is that after going through so many literature survey, these two methods are not incorporated by any of the researchers. Typically, Hilbert and this Wigner wave, this combination is also not used, and the results are found to be better, as we will discuss the results. So, after tried 3-4 different things, short it down as a research work to this typical combination. Classification is used as a SVM for second phase, that is a support vector machine. First phase, so comparing 3 different values at the end for both the current systems, mean value, standard deviation in time domain. So this is a theory for DWT decomposition. So I am converting signal into high pass and low pass filter and getting the expected values this way. Actually, if we check that the bearing frequency, what at the fault, what is recommended on that, for 50 Hz supply, the bearing frequency fault level is somewhere at 69 or 60 to 70. That is a lower frequency range. So typically, a low pass filter signal is carried forward for classifier. This is the way using MATLAB that signal is converted into MAT files. MAT files converted using DWT up to 5 stage, get a mean value, standard deviation, inverse and wavelet domain is obtained. This is the same synthesis. Then feature extraction is reconstructed signal will not have any noise and the other features. It will have only the fault feature. So using this comparison, results can be clearly mentioned that the fault is there and fault is not. This is actual signal, phase 1 signal, normal signal and the faulty signal. The faulty signal, few notches are there but cannot be identifier notches. So I cannot say anything from this that the fault is there. So furthermore, this is a wavelet feature. After applying that, normal signal and the faulty signal is classified in this fashion. Then it is a feature for different RPM. Now one more, in my second paper published, I have tried to check that with speed variation, what is the level of fault variation or the fault signature variation, what is that? So that is also, these are the results for that. The red line indicates with a varying fault. This is amplitude versus the speed. This is mean wavelet coefficients. Here also the drastic change is observed for varying fault and no varying. This is standard deviation. Using a standard deviation also over the speed fault is clearly analyzed. This is a time domain gain, and this gives superimposing of no fault results with a faulty varying results. And with this, one can also conclude that the time domain analysis is not suited for fault featuring. The reason being both the signals are overlap on one or the other. So different separate classifier cannot be used on this. So classification is used with these values. Classification is done using ANN. This is histograph for ANN. This is the selection values for MU and EPOS for ANN. ANN classifier trained data set is given using known values and unknown and everything. Total I have 18 results for faulty and 19 results for non-faulty. Those overall check, and from these 37 results, I come down to actual result sheet at the end that what percentage this method is suitable and another method is not. Phase 2 is a Hilbert vibration decomposition with smooth pseudo Wigner-Wheeler distribution. Feature extraction is SVM. So same signals with faulty and non-faulty are pre-classified once again with this is our input current samples, then first HVD, then SPWD, and then the peak detection is done with a feature extraction. Same signal, faulty, non-faulty. Actually what we do in first vibration decomposition means, say the signal is not a smooth signal. Actually, it is a just go through. It is the same signal. If we closely observe that this signal is not a smooth line, but it is up down, up down, up down. The small variation is there. If I go closely on that, so that close variation with using this spline feature, I am getting a maxima and minima of that wave. It is a portion of that sinusoidal wave. It gives me the maxima and minima of that. Using SP-line function in MATLAB, we can get the upper envelope maxima and lower envelope minima. Also, the average is not shown that, but the average line is also indicated on this graph. Now, this is for faulty and first iteration non-faulty signal. This is a monocomponent first iteration. This is the second iteration for HVD. This also gives little smoothing of the wave. Same for non-faulty signal. Okay. Now what I am going to do, after getting that maximum minima spline, I am subtracting the average value of the wave from that maximum minima and which gives me direct the noise, that is the actual variation at sinusoidal wave which is available on faulty signal and non-faulty signal. Here we can conclude that, say, the non-faulty cycle is throughout, there is no any typical characterization observed on that. This is done using SPWD subtracted with the mean value. This is the second component. So there are two components, first component and the second component. That is the two iterations. So for first component, observation is like this. Second component is the points are more elaborated in faulty and non-faulty. So this is the second component. After that, using SPWD, smooth minerally decomposition, these points are converted into the areas of that, and the plot is formed. And for 10 iterations of this value, faulty and non-faulty signals are formed. This is second component. Here, more classifier you can observe. After this, I am using the image processing dilation tool, and these entire graphs are converted into ones and zeros digital. Dilation means actually I am sharpening those points, and by getting say I am thresholding actually the fault. So converting values into image after thresholding, we get this, and here the clear observation can be, this is for say faulty side and non-faulty side. So the clear observation is there for this value. This is after dilation. Converted value into image after dilation for upper one is faulty, lower one is non-faulty. So fault is clearly observed at typical levels. Removing noise pixels. Once again, if we go for still, actually we are characterizing the fault on both levels. The same analysis is further done for second phase of characterization. So with reference to the speed, what is the variation of fault identification? So this is with fault, this is without fault. So this is the maximum value of monocomponent 1 with RPM. This is plot for monocomponent 1 with different RPM for area number of pixels that comes in value. This is maximum value, monocomponent 2. This is monocomponent 2 for number of pixels with speed variation. After that, SVM is used, support vector mechanism is used for classifier. This actually converts, say in this there are faulty and non-faulty signals. If ANN with its own earlier results it classify with its memory that these are the fault and this is non-faulty. In this case actually the plane is formed which bifurcates faulty and non-faulty signal. So 3D conversion is done in S-plane, and support vector mechanism classifies that. And the conclusion it is based on initiated practice conclusion. Characteristics frequency is proportional to auspicity of the bearing fault. So characteristics frequency is always proportional, something there proportional to the bearing fault can be observed. The energy of the fault increases with a load. Phase 1 and phase 2 provides 88% and 94% of the accuracy. Now these 84% and 94% are observed on that 37 results. Those are given to the classifier, and if the correct, so initially we know that this is a faulty and this is non-faulty. So if it is not identified properly, then it is considered the false reading, and if it is identified 0 and 1 is done for that. So 0 is a fault, 1 is non-fault. If the non-faulty is showing me 0, it means that it's a wrong reading. If non-faulty is showing 1, it's a correct reading. This way percentage is calculated for that, and it gives first phase gives 88% of level, second phase gives a 94% of accuracy. So at the end it can be considered as HVD with SVM is a better option for finalizing the fault Feature scopes. The investigation can be expanded introducing multiple stator and rotor faults. I have done only for the bearing fault. The large size motors are also challenges. The proposed technique may be applied for fault diagnosis for the large motors. Actually, most of the industry, if we go through, gearboxes are as an additional part of the motor, and that also superimpose some impact on direct bearing or the motor. And this is not considered in my studies, that additional components connected to motor and their effect on motor. So that can be also understood. Further scope can be studied later. The additional work is needed to investigate applicability of the other signal processing tools in characterization of fault. So there are multiple tools available. Those are also not studied. I have kept my study to typically SVM, smooth pseudo, and with in this class. There is need to study the effect of electric drives because these may change the current spectrum. Say most of the, in old days, when induction motor was not drastically used, the reason was its speed control characteristics. With advancement in power electronics, I have variable frequency, variable voltage drives, BVVA drives, and all those drives are there. And those drives may superimpose few harmonics in the current of the motor itself. And those are actually not considered in my projects. So that may impact on the methodology, what is investigated in this research. The effect of non-stationary operations on the stator current need to be investigated, and for fault detection of the process. As the last, these are the references. And these are the publications. So actually, sir, initially study was thinking on some TMS processor can be used for this, but actually the real-time analysis is not required, and furthermore, it was not affecting actual cause, so direct current structure. So that's why this is a supporting paper. I am not included directly in publications. Thank you.
In all this diagnosis technique, there are several techniques are there, but Gilbert-Ingham classroom technique.
Yeah.
In your opinion, these are not very investable for the induction motor diagnosis.
My literature survey, there I could not
Because you are looking at a technique. Beyond each and every technique evolve, there will be some philosophy.
Right.
Okay, for what kind of signals or this kind of technique is suitable? How you come to that aspect?
Yeah. Sir, I will let you know. Sir, actually, philosophy is what my internal subdivision is. Say when we we have tried for different vehicles and different type of acoustic noise studies. So actually, maximum in case of bearing, I have gone to escape bearing expert R&D team also. What they have suggested that everything is there on the acoustic base and the vibration base. And if we check typically a motor, when one rotation is there, and if a single bearing spot is creating some typical disturbance on the outer base, then if if we check that for say on the current superimposed frequency of that, we can see that the frequency is going more and more lesser side. So maximum other studies what we check other than the electrical field, where we are worried about the high frequencies, and that to be tackled with, so that we are getting the actual results of the high frequency side. Here the extraction required is on the lower side, and that too on very compact size of it. So basic Fourier transform and all those things are applied, but that will not give a results because entire time domain waveform is very large, and where this bearing fault is showing that, that is the main issue. So we think that the Hilbert, it is considering the vibrations and that too on very minute levels. So this method will implement on higher side. This was the first reason we come across this.
Why you are using AN and SVM? What is the difference?
Yeah, sir, actually we have checked so many papers earlier where it was only feature extraction, but the results of the feature extraction, as an end user, one has to know that the fault is generated or fault is not. So some classifier is needed as an end result of any feature extraction. Otherwise, as a common one who is using later on this machine may not come to know that the fault is there or not.
To me, that these two are fitting each other.
No, I don't.
AN and SVM.
How?
Are they fit each other? Why AN is alone able to do this?
Sir, ANN can do, but the reason is you have to say the basic combination is that for that typical machine, for that typical scenario, I should have some back data to be stored in ANN, and that to get as a prerequisite for fault identification. Then and then only, because I need some exports feature that has to be preloaded, and then ANN will classify all that features. Where SVM, I can classify the things. This was expected.
In that case, you use only SVM. Why you want?
So actually, we have tried with actually we can use for both. Now as a next frame, we can go for the first method with SVM. One of the reasons that can be also analyzed.
Since in your case you are not using the AN and alone for you are going for something SVM.
Right.
Combining AN and SVM, so if you have been told something, some other method is also so you will that.
Yeah, there are so many, but
So how long you continue this? Is there any limits for this?
sir, actually there is, to be frank, there is no limit, because earlier initially we started with only current signature with fault analysis. Then there are Fourier transform. Then there are STFT. Then there are Bingal. There are so there are n number of transforms tried out.
But
So
since you have done research and all those things, you have to be more focused. Which one you want to adapt? Because testing
so second method is more adaptable.
testing several different techniques. He is not a researcher.
Right.
So researcher is always have to go through more in-depth philosophy, how to resolve the issues, and any suggestions. But if already some methods are available, taking this, you will get this. Taking this method, you will get this. In that case, if you are looking at this one, you go through all the methods, apply it to your problem, and what are the pitfalls you should bring out, and in which case, which method fails.
So actually, some analysis I have done earlier in things regarding methods, but because it's a literature survey and time was, so I just, your point is absolutely valid. Sir, these are already carried out work. And problems are also identified. So we are going with that problems to find out something new.
What is new that you think is?
Sir, this way classifier with method is not implemented. That I have checked. Classifier, feature extraction with classifier, this is not implemented.
What about
Why SVM and
what about the wavelet transformation? The wavelet transformation is also.
yeah. So we have used first time DW. This debugging
Wavelet. See, this is a part of wavelet. This is
part of it.
because wavelet will give the time frequency.
Right. So same thing there. Phase one.
So in that case, we have to be little more specific.
More specific.
See, reason is that wavelet transformation for the signature current analysis.
Right. Already done.
People have gone through exhaustive.
Right.
So if you want to show that your contribution is little more ahead of these findings, you have to be little more, some more things you have to bring out. This is my
Right.
observation, one observation. So you have done it, creating this fault and other things. Have you checked any realistic fault in induction model bearings exposed?
Really speaking, no, sir. But I have tried.
See, you this I understand. Your patience is appreciated. But what is the guarantee in the reality? Only this kind of fault will appear.
I agree. Actually, sir, for that purpose, I have tried with one motor rewinding shop.
Understand? Creating that same motor is optical task.
And what I have done, I have initially gathered all the faulty bearings. I have checked what is a ring on that and that. But finally, that cannot be developed because one cannot open the bearing and create a outer face fault like that on real bearing. And using any faulty bearing will give some absurd results. That is also not thinkable.
Another point is that the results somehow whatever you have done, classification and extraction, results are not giving that much confidence on your work. So you have to think what is the way, how, because ultimately when you write something, someone will read, okay, not listen to you.
Right.
So they should feel.
So I should include result table.
Something you have to make more stronger. Should give a thought about results representation.
Right.
How can you make your results convincing?
Right.
Because someone who reads the thesis, he should be convinced.
Right. Actually, what happened, I have only faulty and non-faulty. So I can have 38 readings, 39 readings. So from 39 readings, I can find out the percentage of identifier. So that I have presented, that 84% and 93%. In the last slide, I have concluded that. I will give a clear result of that.
Is it 84, 95%? Can you compute for any machine, any rating, any speed?
Well, it's a prediction, not realistic.
You see, 84%. In that case, you have to add some sentence which is, you cannot generalize.
Right. For this typical machine and this category.
Actually, you should consider, give a thought about this. If I change the power rating,
Right.
if I use for this application, what is the
Right.
if I use a different for same application or different application, if I use under variable speed environment, what would be the generalization that is possible?
Right.
Instead of giving the percentage, AU rate, instead of giving the percentage means what is that in your
So this way, actually test is carried out for faulty bearing. Around 18 sets are developed, 18 different speeds for same motor, faulty, and because keeping some variation, 19 I have kept it for non-faulty. So I have 18, 36, 37. So 37 sets I have total reading with me. Now these 37 sets, I am using the non-faulty bearing case and the faulty bearing case I am using for classifier as a pre-defense. Later on, once again all these things gathered and those are put through process, through Matterfile and check that is it identified. I know that this third reading is of non-faulty. is it classifier identified randomizely? I have said that and check that this non-faulty bearing reading, is it giving me non-faulty or faulty? On that percentage out of 37 readings is carried out. So first method, it gives 84% readings are showing me correctness. That ANN, after finding out, ANN finds out 84% correct readings. And for
Just to give a thought on this point.
yeah.
Somehow I am not confident on the percentage indication.
Okay.
It's not giving me true reading.
Sir, but somewhere
Just think from any other way or
yeah.
this is the first side. The second thing is that you have to make some more attempt how to get the thesis results more convincing.
Yeah. I will put that actual reading
Convincing
thesis
is
reading.
very much required because the results as of now results are not giving that much convincing. You have to take some three-dimensional color plots.
Yeah.
In these plots you have to make it clear what is that you get main important information from these plots, for example.
Yeah. Sir, actually, this is not giving me actual bearing for. This is a process,
Need not because it
Yeah.
is maybe
and it is an in-between process.
in between. What is that if I see if I can read there are two results. What information I can able to get it so that I can able to predict.
Right.
Okay. What
So
are
actually-
the consequences?
Right.
Cause
I will more elaborate.
and you have to elaborate and what will be the reason for this.
Right, sir. Sir, actually, this is an intermediate stage where I am just plotting the energy levels of that. Then I am converting it to 1 zeros and getting the dilation.
Future we don't know. Future always take the past information.
Right, sir.
Some analysis, some understanding, some experience. We will try to say future. Future may not 100% correct. Okay, but at least percentage of correct should be more or less. If you have a more and more experience, you will be able to give the forecast. So here, this my impression is that you have completed these results. Okay, is there any conclusions that you can draw out of these three-dimensional pictures which are intermediate stage from an energy perspective?
Right, sir.
Although these are all these waveforms are electrical quantities, but they are actually representing the physical values. Physical values. So may have some impact on the electrical quantities, but not directly.
Yeah.
It is a indirect impact of
Right.
physical mechanical values.
Actually, all are correct values.
I do not know whether you have studied more on the motion motor quantum diagnostics, particularly bearings. What is the impact of bearings? Okay, variable frequencies. How to analyze these resonance frequencies under bearings under faulty condition. Okay, can you do something about that? Then it will be a good this will be having some value. As of now, you are not included some mechanical aspects. These things you should be included. And finally, I want to ask a last question with that. What is that you want to claim in your thesis abstract?
Yeah.
Bullet points. What that is you want to claim. So one is you have done the experiment, created this one, and applied the AN and SVM technique, and finally classified this structure. Okay, other than this, what is that you want to claim? Because AML is well established, SVM is well established. Okay, future experiments. Okay. So what you have to deep down, because this comes only at the last stage. So during the process, you never notice what is there. So now you
So actually, in medical field, how idea comes to us to use this, that I can share with. In the medical field, for a few say body frequencies and all those things, there this type of HVD and all those things are used. But in electrical field for motor, this is not used. So we thought that this can be.
actually this problem is more mechanically bearings design. So if you as an electrical engineer, if you know what you will do, you will shut down that. You take out the machine from the service, because if if you allow for some more time, your processor is going to unnecessarily suffer.
Right.
As an electrical engineer, what we will do, we will forecast incipient faults, we will try to understand. So then we will replace or we will take a preventive measure. But these bearing problems and these from bearing design point of view, it gives more. What kind of material is better?
Right.
So how much lubrication and what should be the type of valves inside they will use?
Right.
Okay.
So that
They
will be more avoided.
they will decide what is the reliability of and they will ensure of that one. But for as an electrical engineer, we just want to know. Okay. Is it happened? Oh, abnormality is there? We will stop and maintain and that's all. We will not do any mechanical design. Okay. But if you can able to elaborate something, mechanically anything is possible. Any resonance frequency, vibration, anything is going to happen. Okay. If it is a rotor fault, okay, then there is a possibility of uniform non-uniform air gap. In this case, is there any non-uniform air gap will be there? No. So the deviation in the current voltage is very less. Unless unsymmetry.
Eccentricity problem is there that is.
Okay, air gap is uniform. So obviously the flux, current waveforms and all those are more or less sinusoidal. Sinusoidal with
So signature is very small.
sinusoidal superimposed with some noise. Okay. And you should also see what is the guarantee that your sensing circuit is not generating this noise. Are you sure about this? Your sensing
That we have tried. We have done because
see,
I can include that because
you have to include this. Not include that, okay?
Right.
You have to be because under any condition, what is the impact of your sensing circuit?
right. So that we have done initially with CT. I cannot work with because
Whatever you use it, see, but what is the, you have to show that any noise which is coming, okay, is not from the your sensor.
right.
If at all any noise is coming, it is exclusively for your band of operating frequency band. It should be only through the varying fault. You have to show that very clear. Otherwise, you won't give a true meaningful study of this. It is must. Okay. Otherwise, sometimes sensor also will give abnormal frequency components. Okay. If your supply itself is having some problem, that will also reflect on your sensor output. First, you have to be more confident that sensor, because for you sensor is the only candidate where you are taking into data acquisition. Two places, one is sensor, another one is data acquisition. Later on, what you are doing is you are playing with the digital numbers.
That's it.
So this, I think we should look into these aspects.
Thank you, sir.